So we will see here how to solve a binary search tree insertion and deletion. Okay. So initially, what is this binary search tree? What are the conditions it has to satisfy? Okay, so that we will see. So this binary search tree, a node in this binary search tree should have at most of two children. At most means maximum of two children. So a particular node, okay, a node may have a zero child, it may have one child, or at most two child. Okay, either the node may remain without any child, or it may have any one child, or it can have two child. Okay, so that is the first condition in your binary search tree. So the next condition of your binary search tree would be your left and the right child. Okay, the condition that your left and the right child should hold is, suppose you have say for example you have 11 in your root. Your left node should always be lesser to the root. Say for example 7, because 7 is less than 11. Or your right child should be greater than 11. Always it should be greater than 11. Okay, say for example it can be 19. All right. So next, when your when this node has two children, so this has to be less than 7. Say for example 5. Okay, and here it should be greater than 7. Okay, but it should not be greater than 11. See, we are not talking only about the left child and the right child. We are talking about the whole lot of subtree. Left subtree and the right subtree. Okay, so it can be greater than 7. It should be greater than 7, but it should not be greater than 11, because under 11 this is the left subtree. So whatever values comes under the left subtree should be smaller than this number. Okay, but it has to be greater to its parent. You have to see the parent, but you should, when you are comparing with the root, it has to be less. So what number could satisfy here? It has to be greater than 7. It should be, value should be less than 11. Say for example you go for 9. See, it is greater than 7, but it is smaller than 11. So now again, so you have uh, it should be less than 9. Okay, your left should be less than 9. Say for example it could be 4. Okay, because it is, the value is less than 7. All right, and if you see for example, but the value 4 should not come here. Why? Because if you see here, 11 is there, it is a left subtree. Okay, it is a left subtree. For 7, this is going to be the right subtree. So whatever values from 7 towards the right subtree comes, it should be greater than 7. Okay, it should only be greater than 7, but it should not be greater than 11. So this condition is satisfied, but this condition is not satisfied. So if you see 7 towards the right subtree, it should have a greater value, but it should not overtake this particular value. So what value you could fit here? For example, you can fit 8 here. It's a right subtree. It is greater than 7. Okay, it is not greater than 11. Towards the left subtree of 9, you have the value 8. Okay, it is the lesser value towards the left node. Towards the right, you can have the value 10. If you check for the condition, it is not greater than the root node 11. 9 is over here. So towards the right of 9, it should have a greater value. This condition is also satisfied. If you see for the right subtree of 7, all the values are greater than 7. Okay, only thing, it should not be greater than 11. Towards the left, if you see, now you can have the value here. You can have 4 here. Okay, you can have 6 here. So here for the left subtree of 7, if you check, you have a smaller value. Okay, towards the left. For this node, this is the smallest value and this is the greatest value, but 6 is not greater than 7. So usually for your left subtree of 7, all the values holding should be less, and the right subtree of 7 should have a greater value, but it should not exceed 11. It should be, all the numbers should come below to 11. Towards your right, 19 is here. It is greater. So all the values towards your right should be greater than 11. So this is how you have to form a binary search tree. Now we have a set of numbers here. Now we will see how we are going to insert the numbers in a binary search tree. Okay. So initially you have 11. So you take 11. Next number you have 6. Now you have to compare with the root. So 6 is less, so it goes to the left side of the tree. Next you have 8. Okay, 8 you have to compare with 11. It is less, so obviously 8 has to be inserted towards the left side. You go to the next number, you check whether 8 is less to 6 or greater to 6. So it is greater than 6, so you put it towards the right side. Alright, next you go for 19. You check, you compare with 11, you check, it should come towards the right side because it is greater. So you have 19 to be inserted here. Next you go for 4. You check with the root, it should come towards the left hand side. You again check for the next number. It is lesser than 6, so you put it towards the left side of 6. Next you have 10. You compare with the root, it is lesser, so it should come towards the left subtree. You go for 6. You check, 10 is greater than 6, so it should come towards the right. You check for the value 8. It is greater than 8 again, so it should hold the position here. Next you check for 5. Compare with the root, lesser, so it goes to this value. Okay, again it is left, it comes to this place. Okay, now 4 is here, it is greater than 4, so it should come towards the right side. Next you have 17, which should go to the right side because it is great. It is lesser than 19, so it should come towards the left side of 19. Next you have 43. Obviously it should go to that side. It is greater than 19. It goes to the right side of 19. Next you have 49. It should come towards the right side. Next you have 43. It is greater. 49 is greater. So you have 49 here. Okay. Next you have 31. The last number. Obviously should come to the right side. Okay. You have 17. You have, it is greater than 31, so it should again go to the right side of the 19. You check for 43, it is lesser, so you have 31 to be placed here. So this is how you do an insertion in your BST, which is your binary search tree. Okay, now we will go on to the deletion part. Okay, so here deletion is again under 3 conditions. Okay, so you have a node with 0 child. Okay, you can delete a node with the 0 child, or you can delete a node with 1 child, or you can delete a node with 2 child. So now this is our BST. We have inserted all the elements here, and I will draw the same tree here, and I will show you which all nodes could be deleted, which is satisfying this particular condition. Okay, so first let me draw the binary search tree, whatever we have constructed here. Okay, so I have drawn this same binary search tree which we have constructed. Now I'm going to delete the nodes which are going to satisfy these three conditions. So with zero child, so zero child, it doesn't have even one child, means it is obviously the leaf of a tree. So either it could be 10 or 5 or 31 or 49. Okay, so if you are going to delete this particular node, let's say for example 10, in that case if you only delete this link, then you can free this particular node. Okay, you need not you know what, you need not compensate any other number or any other node instead of this position, because after this you don't have any child. So this node doesn't give any commitment to any of the child. It is free, it is already a child, it is already a leaf. After this it has not become a parent. So if you want to delete a node with zero children, it is very easy. Only if you cut this link, you can free this particular node. Okay, that is for a zero child. For one child, for one child condition, which is having one child, say 4 is having only one child. So suppose if you want to delete this particular node, this 4 you want to delete, so what will happen to this 5? We have to think about this 5 when you are deleting this 4. So you have to replace this position with some number. When you are deleting this, you have to replace this position with some number. So what happens, suppose if you delete this link to free this link should be joined here. So this becomes the left child of this 6. Once if you delete this 4, you can build a link here. This will become the left child of this. So this won't be left orphan. It is going and attaching to some node, to the previous one. Okay. So this is how you have to delete one child. When you are going to delete two children, okay, I mean the node which is holding two children. For example, if you go, you can take 43 or you can take 19 because it has
I'm
two child,
confused, like.
or you can take the root node itself 11. If you have to delete this 11, what number should be replaced here? That you have to think before deleting. Okay, so when you are going to delete the node which is holding two child, you have two conditions. One is in order predecessor, okay, and the second condition is in order successor. So you have to find the in order predecessor or in order successor to come and hold this particular position after you delete 11. Okay, so we will again, I will draw this BST or obtained BST here, so that we won't have any confusion of how we are finding this in order predecessor and in order successor. Okay, okay, so we have our constructed BST here. So now I want to delete a particular node which is holding two children. I am going for 11 now because it has left child, right child. Two child it has. Moreover, it has two subtrees, left subtree and right subtree. So if I am going to delete this, which position is going to, or which element or which number is going to take this position, we are going to find. So first we will see in order predecessor. In order predecessor means you always have to go for the left side. Okay, if you are going to replace a number here with in order predecessor method, then you have to go in for the left subtree. Okay, left subtree. From the left subtree, which value are you going to take to fit this particular value? If you are going for the left subtree, you have to choose the greatest value in left subtree. So in this left subtree, which is going to be the greatest value out of all these 5 nodes, you have 10. Okay, so this 10 has to be replaced at 11. When I'm deleting 11, next I have to take the greatest value in this left subtree and put it here. So my tree is going to be like this. This 10 you will get, it will get cut because I have put this value here. Okay, so your in order predecessor, is going to take a form like this. Now we will go in for in order successor. In order successor means you have to go for the right subtree. Okay, in order successor. See, predecessor means previous number. Okay, previous number. Successor means after. So when you had 11 here, something previous to 11 you have to put it at that particular point. Or in the successor means something after 11 you have to put it. So in order successor means you go in for the right subtree because that is holding the greatest value. Here what condition, on what condition you should choose is, in the left subtree you chose the greatest value in the left subtree. In the right subtree, when you are going for successor, you have to choose the lesser value in your right subtree. In right subtree. Okay, so which is the lesser value here? 19, 43, 17, 31 and 49. So you have 17 to be the lesser value. So you replace this 11 with 17. So how your tree is going to be? When you replace this particular node here, when you remove 11 and you replace the node here, you have 17 as the root node. Your left subtree won't change. Okay, it's going to remain the same. Your left subtree is not changing. Your right subtree, this 17 has been gone to the root now. Okay, so you have, as usual, you have 19. Now 17 is not there because that has gone already there. So from 19 you have other nodes, 43, 31 and 49. So this is how your tree will look when you go for in order successor. Or you can go for another method. How are you finding this in order predecessor and successor? One simplest way to write this, you have this tree constructed, right? So this tree, you write it in the ascending order. You take the numbers and write it in the ascending order. Okay. So ascending order means I have 4, 5, 6, 8, 10, 11, 17, 19, 31, 43 and 49. Okay. So you have all these numbers from this tree written in the ascending order. Now you had the root 11. So this was your root, correct? So predecessor, the previous number, that is 10. So that only you have taken here. Okay, in order predecessor value 10. Or if you are going for successor value, you need to take 17. That only you have taken here. So directly you can find out from the left subtree or you can find it from the right subtree using any of the methods which is having two children. when you have two child, in that case you have to go in for either in order predecessor, previous number, or in order successor. So how you can find is, the greatest value in your left subtree will be the in order predecessor, and the smallest value in your right subtree will be the in order successor. If you are getting confused with this method, directly you can write it in the ascending order and see where the root is. The previous number would be the in order predecessor, and the next number will be the in order successor, where you can place it at the root, and same way you can arrange the all other numbers here, except for that particular node in your tree. Other nodes will remain the same position, only those particular nodes will be removed because that is going to the root position. So this is nothing but your binary search tree insertion and deletion.
Yes, so did you all get the video? Did you all understand it? Because for me it was like hanging, the video was hanging, but my voice was clear, so I was not able to follow up the video. So if anybody had the same problem, since I have posted it on the chat, your the video is on the chat, you can just stream it without any interruption so that you can understand it better. So far, whoever could see the video and the audio exactly uh, in a synchronized manner, did you all understand the video of binary search tree? How are you constructing a binary search tree? On what basis?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes,
Okay,
ma'am.
so I will just um, stop the recording.
Ma'am,